Today we're going to be looking at rational functions. And just like, remember, rational numbers were numbers that can be represented as fractions. These are functions that have fractions. So the big key on that it's a fraction is that the variable is in the denominator. That's what makes it a rational function. Now let's remember something. If I have a variable in the denominator, the first thing that we're going to be talking about is how to find the domain. So finding domain, and we've done this before. Finding domain. There was something really special about when we have a variable in the denominator. And that was that the denominator could never, ever equal 0, because remember, that's bad. So let's take an example, and we're going to find the domain of each of these. Okay, so let's take So we're going to find the domain of each of these. And the domain is whatever we want to make sure that the denominator never, ever equals 0. So we'd simply just take that denominator and say we don't want it to be 0. And then solve. So that's x cannot be 3. Over here, we'd have x squared minus 9 cannot be 0. Now we're going to be really careful here because that's an x squared. That means there's going to be 2 answers. Okay, so when I solve and take the square root of both sides, there's going to be a plus or minus. Don't forget the plus or minus. Last one. Well, that's almost like the last one, but there's something weird about that. What's going to happen when I solve? Well, that's a square, it's a negative number. This is an imaginary answer. So, normally when we talk about domains, we're talking about all real numbers. This is not a real number, it's an imaginary number. So that means my domain is all real numbers. Now, when we have these bad numbers in the denominator, when there is a quote bad number for the domain, two things could be happening. I'm going to pause this real fast. I just realized I forgot my graphing calculator at the school, so I'll have to kind of explain what's happening algebraically. The first thing that could be happening is what is called a vertical asymptote. So I'm going to use an example of y equals 1 over x. if you go to a graphing calculator or Desmos, which I just realized I could do, if you have not downloaded the Desmos app onto your phone, it is helpful. So y equals 1 divided by x. I get this graph, and so what's happening there is I've got this vertical asymptote. I've got this split in the graph. So the graph looks like this, and then I've got one section that's doing this and one section that's doing this. What's happening is if I looked at the x values and the y values as we get closer to 0, so if you plug in 0.01 into here, you will get 100 back. 0.001, you will get 1,000. 0.0001 gives me 10,000. So as the denominator gets closer and closer to 0, as those numbers get smaller and smaller and smaller, the y values get bigger and bigger and bigger. So from this side they're approaching positive infinity, and from this side they're approaching negative infinity. So the y's approach either positive or negative infinity. And this is considered the parent function for rational functions. And so there is this vertical asymptote at x equals 0. Whoops, you can't see that. Now I want you to notice something else. There's also a horizontal asymptote, isn't there? We'll get into that a little bit more in just a little bit. Now the next option for what could be happening when we have a bad number. Option 2 is that there's actually what is called a hole in the graph. So I'm going to use, let's see, we got this example. So the first thing I'm going to do here is I'm actually going to factor the denominator. This is the difference of squares, so I'd actually get x plus 3. Sorry about that. The video froze up while I was still talking. The denominator factors into x plus 3 and x minus 3. I want you to notice that the x minus 3's are going to cancel out. And I'm left with 1 over x plus 3. Now, so we've got two numbers that were bad originally, -3 and 3. So I'm going to make a note of that. The bad numbers are -3 and 3. Sometimes if you're doing it in Desmos, you'll need to put parentheses, x minus 3, close the parentheses, then divided by, then you can do x squared minus 9. So let's see what's happening. I see that at -3 I have a vertical asymptote, and that's because x plus 3 is still there at the end, so that's giving me a vertical asymptote. But what's happening at 3? So I'm going to make a table of that function, and let's look at this. At -2, let's see. What's happening when x is 3? It says undefined. And what's really happening on the graph, but we can't see it, is we get a hole in the graph. This is a hole. It's like it can't be 0 over 0. That's just too much for it to handle. And so we get a hole in the graph. So looking at that, it was 1, 2, 3. Here's that vertical asymptote. And we'd have this part of the graph. And then this graph would go this way, 1, 2, 3. But when it reaches 3, it's actually going to have a hole. So whenever you have factors that divide out, you get a hole. So let's make a note of that. When factors divide out, we get a hole. So, what if the instructions say to find the vertical asymptotes? Now, I need to double check my bad numbers to see if any of them are holes, so I need to factor this. Now notice nothing is going to divide out, so both of the bad numbers are going to be vertical asymptotes. So I'm going to have vertical asymptotes. I don't know why I keep losing the video line here. I'm trying to record this at home and it is not doing so well. So this one, to factor that denominator, it's got to multiply to be 6 but add to be 5. So that's x plus 3, x plus 2. So we do have some dividing out here. And I'm left with 1 over x plus 2. So this means there's a hole at x equals -3 and a vertical asymptote at x equals -2. X squared plus 9, we had that up in the intro, and that gave us an imaginary answer. So this means the domain is all real numbers, so there's no vertical asymptotes. Now, we've talked about that there are horizontal asymptotes as well. So I want to show you how you find horizontal asymptotes. Okay, so the steps for finding horizontal asymptotes. Really, what we're going to be doing is divide the leading terms. And when I say leading terms, that means it's going to be the term with the biggest degrees. Now, so there's a few situations, the denominator has a larger degree. So like that f of x equals 1 over x. 1, I can't divide that by x. It's just 1 over x. When we have that happen, we looked at the graph, we saw that the horizontal asymptote, and I'm going to abbreviate that as HA, is always going to be at y equals 0. Let's see what happens if they have the same degree. So my example for that is going to be 3x minus 1 over x plus 2. So I'm looking at the terms that have the largest degree out of the numerator and denominator. That's going to be 3x and x. What happens if I divide 3x by x? I just get 3. Now, if the numerator has a larger degree, there's no horizontal asymptote. It actually might be slanted, or it might be parabolic, but it's not going to be horizontal. Alright, so let's do a couple of examples. With this, we're finding the horizontal asymptote. So here's 3 to try, finding the horizontal asymptote. So when I look at the first one, we have 4x over 2x squared. So when I divide, I'm still going to have an x in the bottom. That means my horizontal asymptote is going to be y equals 0. On B, I have the same degree. So when I divide them, 4x squared divided by 2x squared, I'm just going to have 2. On part C, when I divide, I'm still going to have an x left in the top. And that's going to end up giving me a slanted asymptote. So this is going to be no horizontal asymptote.